All right. So chemistry 3111, where we left off last class was beyond this. However, I saved this question, 18.8b. I said we would try this one today. So I'll just erase that. And the question is, can we make this compound via a Friedel-Crafts alkylation, or do we have to do a Friedel-Crafts acylation and then do a Clemmensen reduction? So let me just separate the two here. We'll just put a line like that. Okay, so we're separated the two. And let's take a look. So if we wanted to make this compound, so this would be isobutylbenzene, what would we do? Well, if we were going to do a Friedel-Crafts alkylation, then we would need benzene, of course, plus we would use this alkyl halide, okay? And then when you react that with aluminum chloride, it's going to give you sort of this positive, oh, I put an extra carbon in there, didn't I? It would give you kind of this positive primary carbocation, but you guys know that that's not going to be stable, right? It's going to undergo a hydride shift like this. And so you're going to get a mixture of alkylation to give you the desired product, but you're also going to get some of this. So where we have something that looks like this. So you're also going to end up with tert-butylbenzene. So you'd end up with a mixture of this compound plus this compound. So tert-butylbenzene. Let's see if I can make that a little bit prettier. There we go. So you'd get both of these compounds. Okay, so you get a mixture of these two compounds. And so we want to avoid that. And so what does that mean? It means we have to do a Friedel-Crafts acylation reaction, okay? Acylation followed by the Clemmensen reduction reaction. So let's pencil down what that's going to look like. I'll do it in blue so it doesn't get confusing. So we're going to start with benzene. Then we're going to use the appropriate acid chloride, which is going to be this acid chloride. So we just count the number of carbons like this. We need a total of 4. Aluminum chloride is going to be our Lewis acid. That's going to give us, put our acyl group in the right place. Sorry, I have a hard time drawing at the bottom of my iPad, but anyhow, there we go. Okay, so now that we have the acyl group installed, we're going to do the Clemmensen reduction reaction. So remember, it's called a zinc-mercury amalgam, so that's why we put the mercury in brackets. And then we need some hydrochloric acid, and you usually have to cook that up, and that is going to give you your isobutylbenzene, like that. Okay, so in both of these cases, it turns out that you have to do the acylation reaction followed by the Clemmensen reduction reaction. So if we go all the way to the end, and I'm probably taking some risks here by doing this, okay, if we look at all the reactions that we covered last class, okay, we covered bromination, and we said not only can you do this with aluminum tribromide, you can also do it with iron tribromide. That will work. We said you can do chlorination, so Cl2 and aluminum chloride. You can also use iron too. Then we talked about nitration, and we said that once you install a nitro group, you can actually reduce it. So if you reduce it, you use iron or zinc as a metal to donate electrons, and then you have hydrochloric acid. But remember, after the first step, okay, so after step 1, since you're in acid, you're not going to get a free amine. What you're actually going to get after step 1 is you're going to get an aniline ion, which looks like this. So it's going to be NH3 plus. Okay, it's the conjugate acid of aniline, and so you have to treat that with sodium hydroxide to deprotonate that. Then we talked about sulfonation to make a sulfonic acid. So sulfonation is this one here. Okay, so this, remember, that's called a sulfonic acid. We're going to see the synthetic utility of a sulfonic acid today. We use it for what's called a blocking group. Then we said you can remove it with dilute sulfuric acid. After that, we looked at, so this is the Friedel-Crafts alkylation. I guess the names are down here at the bottom, so kind of wasting ink here. But anyhow, so Friedel-Crafts alkylation is this one. We covered that. And then Friedel-Crafts acylation is the one that we were just discussing. We discussed the Clemmensen reduction. We also went over this in chapter 17. Now, in chapter 17, it doesn't really talk about excess N-bromosuccinimide, but you guys know that this is a benzylic position. And so if you were to treat that with just a load of or an excess of N-bromosuccinimide, you're going to brominate at every position. And this group is going to be important where you have 3 halogens at your benzoic position. The reason why is because it's a deactivating group, and I'll discuss that with you later on today. So we've covered this in chapter 16. And then we said you could oxidize at the benzoic position to benzoic acid derivatives using potassium permanganate followed by an acidic workup, or you can do this with chromic acid. So if you remember, you can also do this with H2CrO4. I got sulfuric acid on my mind, okay? So you can also do this with H2CrO4, which is chromic acid, but you can make in situ. Anyhow, I'll remove that. And so we've covered pretty much everything on this slide, okay? All of this has been covered in detail. And so what we're going to do now is we're going to talk more about activating and deactivating groups, and then we're going to get into syntheses. And just remember that you're going to have to not only know the reactions that you've already covered in this class, but we're going to have to borrow some other reactions too. So let me just find where we were here. So we covered this, and this is the question that we did. So just to rehash some of what we did last class, we said, okay, if you try a nitration on benzene, it works with nitric acid and sulfuric acid. Remember, we talked about the nitronium ion. Okay, so you need to know the nitronium ion, which is just such a powerful electrophile that when toluene sees it, it's like, hello, you know, it's gonna do a nitration. But anyhow, we said that with toluene, we get nitration at the ortho position and at the para position. We actually get more at the ortho position, and the reason why is because there's two ortho positions. There's only one para position, and a methyl group is actually quite small. Okay. Now, when it comes to the rate of reaction, we said that the reaction of the nitration of toluene is actually faster than the nitration of benzene. And the reason why is that the methyl group is electron donating, right? It's donating electron density into the ring, which makes the ring a better nucleophile. So we talked about that, and we gave an explanation as to why we get nitration occurring at the ortho and para position versus relatively none at the meta position. And for that, we have to look at all of the sigma complexes that are formed from ortho and para attack and meta attack. And you see the two sigma complexes that are highlighted in green. What do they have in common? They have a positive charge right next to that methyl group, which is electron donating. You can see that right here, okay? And we see that when we have not only the ortho attack, but also when we have the para attack. Well, if you look at all three sigma complexes for the meta attack, no such sigma complex exists, okay? The positive charge is never adjacent to that electron donating group. And so what does that mean? It means the activation energy for the nitration at the ortho or para position is going to be lower than the activation energy for the nitration at the meta position. So there you go. So we call the methyl group an activating group. Why? Because it donates electron density, and that's going to come up multiple times today. And then statistically, I said that actually it turns out that toluene is a bit of an anomaly. Most alkyl groups, meaning ethyl, are larger. You're actually going to get more para. You're actually going to get more, come on, pen. You're going to get more para than you will ortho. But with toluene, we end up getting more ortho than para. And the reason why is because the methyl group is so small. So then we said, well, what would happen if we used anisole? Okay, so you see that I have anisole drawn here. Okay, now let me just redraw the molecule of anisole here quickly, just so we can rehash this. Okay, so if I draw a molecule of anisole, okay, you could call it methoxybenzene, but the common name is anisole. So what is the effect of the oxygen on the aromatic ring? Well, there's two effects. Number one, oxygen is the second most electronegative element in the whole periodic table. So yes, it is definitely withdrawing electron density via induction. Okay, so induction. However, it turns out that it's also donating electron density via resonance. And so whenever there's a battle between induction versus resonance, okay, resonance is almost always the winner. So maybe I should cross this out. So I'll cross this out. And I'll say resonance almost always wins, and it does in this case. And so it turns out that the oxygen from the methoxy group actually activates the ring and makes it 400 times more reactive than toluene. Okay, so we see the resonance forms here. You can take the time to draw those. And what I told you last class is that it turns out that anisole is actually so reactive that you can brominate it, and it brominates everywhere. It brominates in both ortho positions and the para position, right? Activating groups activate to the ortho and para positions, and no Lewis acid required. So no Fe required for this reaction. You don't need it at all. And this reaction is actually going to come up later on in this chapter and maybe in another chapter as well. Now, for our class, so for chemistry 3101, or sorry, 3111, what we are going to assume is that if you did this reaction, you're only going to get the monobromination, okay? And it's going to be at the para position. So this is what we would assume. We would assume you only get this. So for chemistry 3111, okay? So you don't have to worry about, oh man, I'm going to, halogenate this thing everywhere. But again, what's kind of the take-home message? We looked at benzene, then we looked at toluene, which had an electron donating group, and then we looked at anisole, which had an electron donating group. Both of those react a lot faster than benzene, so we call them activators. And you notice that both activators were ortho-para directors, right? They directed all of the substitution to occur at the ortho position or the para position. So statistically, for the anisole, it turns out that most of the nitration or substitution would occur at the para position, and that's because the methoxy group is significantly larger than the methyl group. It's got free rotation, and so it blocks out the ortho position. So if we take a look at the sigma complexes, it's the same pattern in a way that we saw for the toluene, in that we have two extra resonance contributors when we look at the sigma complexes that are formed from ortho attack or para attack. You see them highlighted here in green, and I went over them with you last class. When you look at the meta attack, there's only 3 resonance contributors, and so that explains why the activation energy for substitution, in this case nitration, at the ortho position or the para position for anisole is so much lower than the activation energy for nitration at the meta position. All right, so this is all things that we covered last class. And so what I wanted you to read for today was the section on deactivating groups. And a deactivating group, you can imagine, is the opposite of an activating group, in that deactivating groups are not electron donating, they're electron withdrawing. Now, what's one of the most electron withdrawing substituents you can even think of? One of the most is a nitro group. Nitro groups are extremely electron withdrawing. There are others, and we'll take a look at them, but nitro groups are notorious for being very, very electron withdrawing. Now, why would that be? Okay. Well, first of all, you can see that there's a dipole between the carbon of the aromatic ring, this one here, and the nitrogen, because nitrogen is more electronegative than carbon. And also the nitrogen has a positive charge on it, so it's hungry for electrons. So you have a strong dipole there. And then if you draw all the resonance forms, you can see how it's pulling electron density of the ring. Now, if you're saying, well, how do I know that? Well, look at this. Here's a clue. Here's the aromatic ring with a positive charge in it. Does that look like it's got a lot of electron density in it? No, it's positively charged. It's starving for electrons. So it's electron deficient. And so again, the nitro group is pulling electron density out of the aromatic ring. So what's the effect? Twofold. Number one, in terms of reaction rate, check this out. You're going to love this one. Nitration is 100 times slower with nitrobenzene than with benzene. So if you were to compare this compound, this reaction, okay, versus the nitration of just plain old benzene, this reaction is 100,000 times slower. So you can imagine it's not the greatest reaction. I mean, it works, but you have to heat it up with strong acid at 100 degrees Celsius. Okay, so you have to hit it with a pretty big hammer to get it to work. However, not only is it slower, but look at the mixture. We get almost none of the ortho and para products, but we get almost exclusively, I mean 93% in this case, that's almost all of it, is converted to the meta product. The meta product is the major product. So what we're going to see here is that deactivators, generally speaking, are going to activate to the meta position. Now, why would that be? I bet you know why. It's got something to do with the sigma complex, doesn't it? If you take a look at the sigma complexes that result from the ortho and para attack, remember, these are disfavored, okay? When we were talking about activating groups, everything that was circled or highlighted in green, those were extra resonance forms or more stable. These two on this slide, now that we're talking about deactivating groups, these are destabilized or less stable sigma complexes. Now, why would this be a less stable sigma complex. Let's think about it. You've got an electron withdrawing group, a nitro here, and then you've got a carbocation next to it. Good night. That is not stable at all. Okay, this doesn't even want to exist. And then if you look at these resonance forms here, these sigma complexes that result from the para attack, you see the exact same thing happens. We end up with a positive charge adjacent to a nitro group. That is highly unstable. So you could just put here unstable exclamation point. However, when we look at the sigma complexes that result from meta attack, check these out. We don't get any of them where the positive charge is adjacent to the nitro group, right? They're always at least one carbon away from the nitro group. So that's the rationale. That's it. Give me a thumbs up if you're with me on that, even part of the way. Great, awesome, awesome. Not an elementary concept, right? Because you have to understand resonance, mechanisms, activation energy, a lot of different moving parts here. So if we look at the activation energies for the nitration of nitrobenzene, what do you see? The activation energy for the meta attack is a lot lower than that for the ortho attack and para attack, right? Look at this. I mean, this thing is just massive, you know, activation energy here. So there you go. So that's the kind of the point here. Now, it wouldn't be organic chemistry if there wasn't some kind of exception, would it? Right? Okay. So what I told you was, so far the take-home message is if you have an activating group, so which is usually going to be some kind of electron donating group, you're going to activate to the ortho position into the para position. If you have a deactivator, it's going to be an electron withdrawing group like a nitro, and it is going to direct to the meta position. But there is an exception, and that is the halogen. So check this out. It says here the halogens, okay, and you guys know the halogens, fluorine, chlorine, bromine, and iodine, okay, they do withdraw electron density because of electronegativity, right? So they do pull electron density away from the ring. However, they can donate electrons through resonance. So check this out. It says here, halogens withdraw electrons via induction. There's not anybody in here that couldn't draw, you know, this right here and say, okay, well, you got chlorine, it's electron withdrawing, or maybe you could think about bromobenzene, right? You could draw the same kind of thing here where you have your electron withdrawing group, et cetera, et cetera. But then if you take a look at chlorobenzene and you think about all the lone pairs on it, right? 1, 2, 3, 4, 5, 6, right? 3 lone pairs. Well, you could also draw these resonance forms where you show the electrons being donated. And what do we see here is that we have negative charge in the ring. And so then there's a battle between induction and resonance. And what I told you is that when there's a battle between induction and resonance, that resonance usually wins. Well, there's an exception here because induction wins. And it turns out that the halogens are deactivating. They are deactivating. However, so again, this is why they're an exception. They are deactivating. There's no arguing that. But what do you notice is that the negative charge on the ring is in the ortho and para positions. So they are deactivating, but based on resonance, and you'll see this with the sigma complex in a second, they direct rather to the ortho and para position. So check it out. If you look at all the sigma complexes that result from the nitration of chlorobenzene, if you look at the ortho and para attacks, what do you see? You end up with one extra resonance form in both cases where the positive charge is not in the ring, but it's on the actual halogen itself. You see it here and here, okay? However, if you look at meta attack, you don't see that. That extra resonance structure is missing. It's not there. And so there you go. So let's rehash. The halogens are electron withdrawing via induction, and so they are deactivating. However, because of their resonance forms, okay, shown here from their sigma complexes that result from the nucleophilic attack, if you look at the ortho and para attack, you get one extra resonance form that you don't get with the meta. So there you go. So now that we've covered 18.7, 18.8, and 18.9, so we've covered this. So if you're keeping track, we've covered 18.7, 18.8, and 18.9. Now we're going to kind of put it all together in 18.10. And sometimes students will ask me, do you have a summary of this or something? Well, that's kind of what section 18.10 does, is it provides you with a summary of what we've just talked about, and it gives you a little bit more information. So let's go through it. And what I'm going to tell you in the end is, after I go through all this information, I'm going to say you have to kind of know table 18.1. But you're not just going to stare at the wall and try to memorize this. There is a rationale to all of it. So my job right now is to walk you through all the rationale of the activating groups and the deactivating groups and explain why they are what they are to you the best I can. So first of all, you probably notice some commonalities with all the strong activators, whether it's a phenol, phenoxide, aniline, some kind of substituted aniline or disubstituted aniline. What do you notice is that the atom that is attached to the aromatic ring, they all have a lone pair on them, right? They have a lone pair here, 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 and here that is not delocalized outside the ring, okay? They're delocalized inside the ring. You could sit here and draw the resonance forms for any of these where you show the lone pair being delocalized inside the ring. Yes, you could do that, but the lone pair is not delocalized outside of the ring. So we'll say here, lone pair delocalized inside ring, but not delocalized outside of the ring. And so, yeah, that's going to make the ring more nucleophilic, right? You think, okay, well, I could draw a resonance form like this. Well, that's going to make this more nucleophilic, right? Well, it turns out that when you have an atom next to the aromatic ring that has a lone pair on it, like an oxygen or a nitrogen, however, when there's a carbonyl right next to it, okay, well, that is still activating, right? Because you could draw the lone pair as being deactivated inside of the ring. Yes, you could do that. However, you could also draw the lone pair as being delocalized outside of the ring. And so these are still going to be activators, but they're not as strong activators. So we see this ester and these amides here. And then if you're wondering, why is the alkoxy in here, right? Shouldn't it be up here? That's a great question. And it turns out that the methoxy is like the strongest of the moderate activators. It's actually kind of somewhere in a no man's land, I would say, between strong activator and moderate activator. So out of all of these, yes, the alkoxy group is going to be the strongest activator, but for other reasons that aren't really discussed in the class, it's not as strong as the other strong activators. Anyhow, let's move on from there. What's a weak activator? That would be an alkyl group, whether it's methyl, ethyl, isopropyl, tert-butyl, sec-butyl, whatever, okay? Any alkyl group. Because you remember, the alkyl groups are electron donating, but they're only electron donating via hyperconjugation, which isn't really discussed in any detail in our textbook. So you don't have to go on some kind of diatribe about that. But they are going to be weak activators. So now we've covered the strong activators, the moderate activators, and the weak activators. And what do they all have in common? Well, if you were looking at the notes, you'd notice that every single one of these activators, they're all ortho-pair directing, right? They all direct to the ortho position and the pair position, every single one of them. Give me a thumbs up if you're on with me on that, or just, I should say, does anybody have a question on the activators? So right now we're just talking about activators. Don't worry, we're going to get to the deactivators in just a second. Okay, cool. So there you go. So those are things that are going to activate the ring towards electrophilic aromatic substitution. Let's talk about some deactivators. The strongest deactivators, well, I told you that nitro is a very strong deactivator, and it's probably the most common one that we see. The next one is if you have some kind of anilinium ion here. So if you have some kind of nitrogen that has a positive charge because it's got 4 bonds on it. And again, we will see this show up in the class. So not anytime soon, but we will see it show up. And the last one, if you remember on the slide that we talked about a few minutes ago, I said that if you took something like toluene, so I told you that if you took toluene and you treated it with excess NBS and heated it up, you'd end up with 3 bromines here. So there's so many halogens, 3 of them that are all electron withdrawing, and so it deactivates the ring. Okay, so those are strong deactivators, but again, the one that we're going to see probably 90% of the time will be some kind of nitro derivative, and the nitro is actually going to be important in a few other things that we're going to look at today. When we get to moderate deactivators, I know you all are very astute when it comes to science, and I bet you can all recognize the commonality with everything that's a moderate deactivator. What do you notice is that they all have some kind of pi bond, right, at the benzylic position. So at the benzylic carbon, or whether it's a sulfur or whatever, they all have some kind of pi bond on them. And so you could spend your time drawing, resonance forms for all of these where you show the electrons from the ring being delocalized outside of the ring. And so what does that mean? They pull electron density away from the ring, and so they're deactivating, okay? And we can see here we have a ketone, aldehyde, ester, carboxylic acid, amide, sulfonic acid, and this is a nitrile here, right? So you guys should know that C triple bond end, this here, that's a nitrile. So all of these count as deactivators, but these are moderate deactivators. And then the weak deactivators, it's just the halogens. The halogens are weak deactivators, but remember, they're an exception because they don't activate the meta position, they activate the ortho and para position. And if we go back here, I didn't really summarize it, but I've talked about it a few times already today, is that the strong and moderate deactivators, they're going to direct to the meta position. It's just the weak deactivators, the halogens, which are an exception, which donate or activate the ortho position and the para position. So everything is summarized on table 18.1. I recommend printing a copy of this out and putting it somewhere so you can review it over and over and over, until you can't look at it anymore. But again, there is a rationale. There is a rationale to it. Okay, so there we go. So there is a rationale to everything here. So we have our strong activators at the top, then moderate activators, weak activators are alkyl groups. Then we said the halogens. The halogens are the exception. They are deactivators. However, they activate to the ortho and para position. Then we have our moderate deactivators, and then we have our strong deactivators. Okay, now there's a lot of information in what we just covered. There's a lot of information on this slide. Okay, I'd be a liar if I said there wasn't. So what are we going to do? Okay, let's see. What we're going to do is we're going to try some practice here to see if we can flesh out some of the ideas and see how it would be useful for us, okay, as organic chemists. So let's start with 18.16. There's nothing easy in organic chemistry, that's for darn sure. However, this one here just gets us into some practice about identifying activators, deactivators, and whether it's strong, weak, or moderate. Okay, so it says for each of the following compounds, you can see they're all monosubstituted benzenes, predict whether the ring is activated or deactivated, then predict the strength of activation or deactivation. Excuse me. And then finally, predict the expected directing effects. Okay, so let's do all three. The first one is a nitro group. I'm going to go back to the table, and you see that a nitro group is a strong deactivator, and therefore it's going to be a meta director. So let's go back here. And so what we're going to do is we're going to write three things down. We're going to say deactivator. We're going to say strong, and it's going to direct to the meta position. The next one, we have a carbonyl, right? We have a carbonyl directly attached to the aromatic ring. And so you can see how that could pull electron density out of the ring. And so this is going to be a deactivator, but it's not one of the three strong deactivators. In fact, you notice the acyl groups are moderate deactivators. So we're going to put here deactivator, moderate. And then if it's a deactivator, we're going to say meta position, unless it was a halogen, in which case we have in the next one. So remember, the halogens are an exception. They are deactivators. They are weak. So we'll put here deactivator, put weak. But they don't direct to the meta position. They direct to the ortho and para positions. All right. Now the last one is something that we didn't see directly on that table, did we? But remember, as an organic chemist, you have to be able to assess the situation. And you notice that you have a double bond to the nitrogen, which is an electronegative element, kind of like a carbonyl in a way, and that's at the benzylic position. So you can imagine that you could draw a resonance form like this, okay, where you'd have a negative charge on the nitrogen and you would show a positive charge inside the ring. If you don't believe me, we could just draw the resonance form of this quickly. Come on. There we go. So let's just scribble it down here. It would look something like this. Okay, and then we would have a negative charge on our nitrogen. So it's going to look something like this and something like that. So there you go. You can clearly see that there's electron density being pulled out of the ring. However, this is not a strong deactivator. It's not a weak deactivator. This would be a deactivator, but it's moderate. So we'll put here deactivator and moderate. And if it's a moderate deactivator, it's going to direct to the meta position. So there you go. So now all we've done is we're kind of just working on table 18.1. So if you go back, it's this table here. So we're just going to write here, we'll scribble down table 18.1, and I'll put a star in there because you need to either memorize it or at least familiarize yourself with it enough so that you know how to apply it. All right. Give me a thumbs up if you're with me on that. Just kind of the information in table 18.1. Okay. I agree there's a lot of information to summarize in there. I'd be a liar if I said there wasn't. There's quite a bit of information. But again, the way David Klein presents it in the textbook is he tries to put a rationale to it. Okay. So now what we're going to do is we're going to kind of switch gears a little bit, and we're going to talk about not just having one substituent on your aromatic ring, but what happens if you have two? Like, how is the ring going to be activated if you have, let's say, two alkyl groups, a big one and a small one? Or how is the ring going to be activated if you have like an activator and a deactivator both attached to the ring? And those are great questions. And that's what we're going to try to uncover right now, okay? Because we're going to look at all kinds of compounds that have two substituents on them, an aromatic ring with two substituents. And so let's walk through it. So follow along with me here. The directing effects, so I'm reading from the top, of all substituents attached to the ring have to be considered in an electrophilic aromatic substitution reaction. So what we have to do is we have to look at the methyl group. We have to look at the nitro group. Let's imagine there's a halogen, right? We have to look at that. We have to look at everything and make an assessment of that group, okay? So it says the directing effects of the methyl and the nitro in this compound here, meaning this compound here, direct the bromine to the same position. So let's think about this. The methyl group, right, that is a weak activator. It directs to the ortho position and to the para position, but there's already something there, okay? Whereas the nitro group, that's a meta director, but it's directing to the exact same place as the methyl group. So of course the bromine is only going to go ortho to the nitro and ortho to the methyl and meta to the nitro. Give me a thumbs up if you're with me on that. Any questions about this particular reaction? Okay, it's a good one, right? If you wanted to make this, I mean, this reaction is going to work really well because both groups are pushing the bromine to go to the exact same place. Okay, that's great. But what if your groups are directing to different places? Okay, because that could happen. Well, it says here, if the groups on the carbons, if the groups direct to different carbons, what do you go with? How do you break the, how do you figure out where it goes? It says right here, the stronger group will dominate the directing effect. So here on this compound, so this would be paramethyl phenol, you've got the hydroxyl, which is a strong director, right? So this one is strong. And then you have the methyl, which is an activator. It's an ortho-para director like the hydroxyl, but this one is weak. So if it's a battle between something that's strong and something that's weak, who's going to win? Well, the strong group is going to win. So this hydroxyl group is donating or directing, I should say, to the ortho position into the para position, but the para position is blocked by the methyl group. And so the nitro is going to go ortho to the strong directing group, and it's going to go meta to the weak one. Give me everybody with me on that one. Can I get a thumbs up on that one? I just want to take it slow to make sure everybody's with me on the concepts. All right, cool. So now what we're doing is we're taking table 18.1 and we're really trying to flesh it out. Like, how do these different groups work together, okay? So we figured out the first one. They both directed the same position. We figured out this one where they directed different positions. So who wins? Well, it's the group that's stronger. And then what if you have a mono-substituted ring, okay? Like, let's say you have isopropyl benzene, like this compound here. This is an isopropyl group. What I told you was, except for toluene, which is methylbenzene, the para product is always going to be the major product, okay? And that's based off of sterics, right? Because there's free rotation around this bond, okay? So the para product is going to be the major product. Let's see here. Again, the only exception would be toluene, okay? So there is, I'll just put here exception, would be toluene, where you're going to get mostly ortho product. All right, so let's take a look at this one. Now, what if you have two alkyl groups, right? Here we have an isopropyl, and then we have a methyl. Both of those are weak activators, so who's the winner? Well, let's check it out. It says for 1,4 disubstituted rings, substitution will occur at the less sterically hindered site. So you can clearly see that the position that is ortho to the methyl group is less sterically hindered than the one that is ortho to the isopropyl group. And so that's going to be your major product. So again, if you have two, weak activators like two alkyl groups, what's going to be the deciding factor here? It's going to be sterics, right? That's all it is. Okay, you look for whichever position is less sterically hindered. That's your winner. And then what if you have a 1,3 substitution? Okay, it's a great question. First of all, you're not going to get any substitution between the two groups. Okay, this position is going to be really hindered, so you never get anything there. Typically does not go between the existing substituents. So what it's going to do is it's going to go ortho or para, in this case, ortho to the smaller substituent. Okay, so the methyl group is a smaller substituent, so it's going to go ortho to the smaller substituent, not ortho to the larger substituent. Okay, so that's the third one, and I think that's it. So to keep going, let's say, so now we're kind of switching gears again. Okay, so if you're not following me, let's back up. What we just did is we went through all the activators and deactivators. Then we went over the rules for if you have, two groups that are directing to the same position. That one's, I don't like to use the word easy, but it's good. It's just going to go to that position. If there's a battle between strong and weak, the strong is going to win. We said if you have a mono-substituted ring, it's usually the para product that's going to predominate. If you have 1,4, it's going to go ortho to the smaller group. And if you have 1,3, it's going to go ortho to the smaller group. It's never going to go in between the two alkyl groups or two groups. Okay, so now we're switching gears again, and we're asking ourselves, is there a way to do this reaction? Okay, so we're going to talk about something new now. Okay, we're switching gears again. So I'm starting it with tert-butylbenzene, and you guys know that this is an alkyl group. It is a weak activator, and weak activators activate to which position? They activate to the ortho positions and to the para position, but this is a big group, right? A tert-butyl is big, and so you would think that if you were to treat this compound with iron and bromine, that you're actually going to get just a whole bunch of this compound. So what would it be? 4-bromo tert-butylbenzene. That's what you think you would get, is nothing but that. However, there is a way to make the ortho compound, and the way to do that is to install what's called a blocking group. Now, it's not a protecting group. That was something else. A protecting group was used to actually mask a functional group. There's no functional group in this compound, so we can't call it a protecting group. We just call it a blocking group because what we want to do is we want to block the para position, okay? And if we can, I'll use my green pen here. If we can block this position, then we won't get anything there, and it will all go in the ortho position, right? Because remember that this is an ortho para director, right? It's a weak activator. So the strategy would be what's shown at the bottom, okay? First, you're going to install your blocking group, you install your bromine, and then you remove the blocking group, and ta-da, there you go. So now you're going to discover what the utility of the sulfonic acid was. So now you know why we learned the concentrated fuming sulfuric acid. Check it out. Remember, if you use fuming sulfuric acid, which is a mixture of sulfuric acid and sulfur trioxide, you can make a sulfonic acid. To review, this group here is called a sulfonic acid. It is a moderate deactivator, and therefore it's a meta-director. Okay, so it's meta-directing. So what does that mean? It means that if we could install the sulfonic acid at the para position, the sulfonic acid is directing to the meta position, and the tert-butyl group is directing to the ortho position. So they're both directing to the same position. You put in your bromine with your bromine and iron 3 bromide, and then you use dilute sulfuric acid to knock it off, and you're done. That's it. So this, again, this is what we call a blocking group. And remember, it's not the same as trimethylsilane, which is a protecting group. because a protecting group protects some kind of functional group. This is just blocking a position. It is not protecting a functional group in any way. So now what we want to do is we want to switch gears slightly, and we want to look at these compounds here, and we want to make some judgment calls. It says for each of the compounds below, identify the positions which are most likely to undergo an electrophilic aromatic substitution. So let's take a look, and I'll try to use my colored Apple pencil. So I have a methyl group. Now I know a methyl group is a weak activator, so it's going to direct to the ortho and para positions. The ortho positions are blocked. There's groups there, so it's going to direct to the para position. And then the nitro groups are strong deactivators, and they're going to activate to the meta position, and their meta position is right here. And so therefore, this is the spot that is going to be activated. Give me a thumbs up if you're with me on the rationale for that. Cha? All right, awesome, awesome. So now what I'm going to do is I'm going to redraw this molecule just so I have a little more room to work on it. So the way they drew it was like this. So I have my methyl group here, which is a weak activator. I have my nitro groups, which are strong deactivators. Okay, so let's figure this out. Now the methyl group is stronger. So even though it's weak, it's still stronger than any deactivator. So it's directing to the ortho position and the para position. But remember that two of those positions already have substituents, so it's only really directing to this position. And then this nitro group is directing to this meta position and this one, but this one has something on it. And then this nitro group is directing to this meta position, which has something on it, and this one here. So what's the take-home message? The spot that's activated is this one here. All right, let's take a look at the next one. So the next one's a little bit more involved. We have, let's see, let's start with the moderate activator. The moderate activator in this one is going to be this one where I'm drawing in the blue lone pairs. It's going to be this ester, right? These are both esters, but they're connected in different ways. The aromatic ring is connected to the sp3 hybridized carbon here, whereas the aromatic ring is connected to the carbonyl here, right? So this group, this whole group here, is going to be a moderate activator. Let's put here moderate activator, like that. Whereas this group over here is going to be a moderate deactivator. So we'll put here moderate deactivator, like that. Okay, and then we have the methyl group, which is a weak activator. So I'll just put here weak activator, okay, like that. So now let's figure this out. We'll start with the strongest one, which is the moderate activator. So the moderate activator is going to direct to the ortho and para positions. Two of them are blocked. The only one that's open is this one here, okay? The moderate deactivator is going to direct to the meta positions. One of them is blocked, the one with the methyl group on it, but this one is open. And so the methyl group is going to direct, it's going to direct to this position. I'll use a green pen. Where's my green? It's going to direct here, which is blocked, here, which is open, and here, which is open. But those, remember, the blue is a moderate activator, so it's stronger than the weak activator. And so the blue one is going to win. And so the activation is going to be at this carbon here when we make that judgment call. Everybody with me on that one? Anybody? Thumbs up on that one. Okay, they get a little bit more tricky, okay, but you have to evaluate every group. Okay, let's try one more. One more. You should remember that a nitrile, so if we go back in the table, if you go back to the table, you can find the nitrile is in here. Come on, table, where are you? The nitrile is right here. It's a moderate deactivator, so it's going to be a meta director. So let's go back to our problem. Where was it? Here we go. So let's zoom in, and this is going to be a moderate deactivator. And so it's going to direct to the meta positions, which are here. And then we have the methyl group. There's two of them, but that is a weak activator, which is going to be the strongest activator on here, and it's going to direct to the ortho positions. So that would be here and here, and then it's also going to direct to the para positions, which are the same blue circles. And so either one of these is going to be the position that is going to be activating. So there we go. So now we're able to look at all these molecules, look at the groups that were attached to them, determine whether they were weak or strong activators, and then whether they were ortho or para-directors. Remember, if you have a weak activator, it's going to win over a strong deactivator. So activators always take precedence over deactivators. Well, with that in mind, let's take a look at 18.20. It says here, for each of the following compounds, determine the position that is most likely to be the site of an electrophilic aromatic substitution reaction. Okay, so what I'd like you to do is try this one on your own, and then we'll take a look at it after our first break. And then I want to try one of these problems with you before we take our first break. So let's take a look at this synthesis here. Okay, we want to take isopropyl benzene. So I don't know if I've told you this or not already. I have a hard time remembering everything I say in class. But if you look at isopropyl benzene, it has a common name, which is cumene. The only reason I tell students that, it's not part of the content of the course, but the author of the textbook loves this as a starting material so much that, yeah, he uses it all the time, so you might as well know the name. Anyhow, so we know that the isopropyl group is a weak activator, and it activates to the ortho positions and to the para position, but we know that it's going to activate more to the para position. Why? Because of steric hindrance, right? This is a big alkyl group. And so if we want to put a nitro group ortho to the isopropyl group, what does that mean? It means we have to install a blocking group, right? And our blocking group is always going to be a sulfonic acid. So let's put here, we're going to put need blocking group. All right, so we need a blocking group. So let's start the synthesis. We're going to take our isopropyl benzene or cumene, either one is fine. We're going to treat that with fuming sulfuric acid, so fuming H2SO4. That's going to install the sulfonic acid at the para position, so it will block, or it will be blocked, so SO3H, like this. So there's our sulfonic acid. I don't know if I told you guys or not, but I'm getting so many calls from telemarketers. It's just mind-boggling. Anyhow, so where was I? We have our blocking group installed. So now we're going to do our nitration. So for that, we need a mixture of nitric acid and sulfuric acid, like this. So that's going to put in our nitro group. Mr. Dion. There we go. So we're going to have isopropyl here, we'll have the nitro here, and then we'll have the sulfonic acid. And then to get to the final product, all I have to do to remove the blocking group is treat it with dilute H2SO4. It's actually a question about that mechanism in the textbook. And I don't know, I'm pretty sure I've told you this before, but I don't say it every day. So in case you've forgotten, if you draw a mechanism going in one direction, if anybody ever asks you, what's the mechanism for the reverse? It's always the exact same, just in the opposite direction. So all you have to take is take all your curved arrows and draw them backwards, and that's the reverse mechanism. It's based off of something called the principle of microscopic reversibility. So now what I want to do, before we get into section 18.12, where we start talking about synthesis, is I'd like to take a short break. I'd like you to try 18.20. So give this one the old college try. And I want you to see if you can affect this synthesis here, which you can already tell doesn't require a blocking group in this case. So it's a pretty quick one. But anyhow, it'll give you some time to practice this. And then once we get through our break, we're going to take all these reactions and we're going to really work on them hard and think about making molecules like this one, where we have a bromine and a nitro group that are meta to each other. And so we're going to ask ourselves, which one of these groups are we going to install first? So now it's not just a matter of knowing our reactions. The order starts to become very, very important in here.